This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Dynamics. In today's lecture, we will see PISO algorithm, which is pressure implicit with splitting of operators. So, this PISO algorithm is used for unsteady simulations or the transient simulations of CFD. And in the previous session, we have seen simpler algorithms where these algorithms are used for steady state simulations. Okay, so before that, let us actually recall what is steady state and what is transient simulations, and then we will just revise what is simple algorithm, simpler, and then we'll go to what is PISO algorithm actually. So we'll just do small recap and then we'll go for the PISO algorithm. Okay. So here, before starting the simple algorithm, so we have steady state and transient. So what is the meaning of steady state? So steady state. So steady state in the sense we have time derivative terms in the equations. So equations in the sense what? Continuity equation, momentum equation, energy equation. Let's say dou rho by dou t plus del dot u, or let's say v, equal to 0. So this is a continuity equation, full form of continuity equation. So when I say the steady state or the steady state equations, okay, then the time derivative terms so will not be present. Okay, we will neglect the time derivative terms actually. Fine. So other space derivative terms are available. Okay, so that is steady state. When I say transient, so the full form of equation will be available. Okay, so transient simulation or unsteady simulation, both are similar actually, where your flow variable, you take a density, so which is function of x comma y comma z. So this is for steady state. Now for the transient, so what happens? X comma y comma z comma t. So this is for the transient. So this is the difference. That is the difference between steady state and transient. Okay. So here in the simple algorithm, so what we have seen, so simple algorithm is semi-implicit pressure linked equation. So here what we have seen the guess value initially of the pressure. Let's say, so this one we substituted momentum equation. So when we substitute that P star is nothing but initial value of guess. And when we substitute in x momentum, so x momentum equation and y momentum equation, what happens actually? So when we substitute in x momentum equation, y momentum equation, then we will get the value of V star. Okay. So once we get the value of V star, so then we will introduce the pressure correction term, P dash. So what do you mean by P dash actually? So you have some correction factor. Let's say you have some changes in the initial case value. So that correction factor you will apply, and then you will calculate what is the value of V, actual velocity V. Okay. So how? So basically we will get P is equal to, let's say, P star plus P dash. Okay. So this P dash or P naught, so this thing can be positive, or let's say the magnitude can be so decreasing pressure. So that is depends actually. So this plus value can change. So it can have minus also, but depends on the type of guess value we have or the correction we have. This value changes. Fine. So then what happens once we get the actual value of P? Then the whatever the correction we have got. So what, because of from the P dash we will get let's say U dash and V dash. Okay. So from the pressure correction equation, like we will get the velocity corrections along U velocity, along V velocity. So therefore what we get, so U is equal to, so U star plus U dash. V is equal to V star plus V dash. So this is what we have. Fine. So whatever we get, the actual values of velocity p, u, v, then finally we'll substitute in the continuity equation, and then we will use it for the temperature equation, turbulent kinetic energy, and the internal energy equation. So then we will check for the convergence criteria using the residue. So how do we see? So basically modulus of, let's say, u of I plus 1 minus u of I. So what is the meaning of u of I plus 1 minus u of I? So u of I plus 1 in the sense the current value or the next value. So I, u of I is nothing but the previous value. So let us take I is equal to 1. What happens actually, it is u2 minus u1. So the difference between the next value and the current value is nothing but u2 minus u1. So when it has done, then what happened actually? So you will set up a convergent criteria where the difference between u2 and u1 is less than or is less than 10 power minus 6. So what happens? Then it will stop. So if it is greater than 10 power minus 6, it will go for the second iteration. Let's say this is first iteration. For the second iteration, whatever the output values we get from the first iteration, let's say p value or v value or let's say u value, so these will be as input for this second iteration. So from here we will be taking it. Okay, so this is what happens in the simple algorithm. Okay, then we have a simpler algorithm, the extension of simple algorithm, where we will start the simulation with the initial guess of pressure and gas velocity of u, gas velocity of v. Then we will substitute those values in the discretized momentum equation. So what is discretized momentum equation? So we have u of I comma j to the power of n plus 1 minus u of I to the power of n divided by delta t plus u of I into, let's say, so u of I plus 1 comma j minus u of I comma j divided by delta x. So this is what we have. So this is one of the discretized equation which I'm saying, I comma j. So p of I plus 1 comma j minus p of I comma j divided by delta x. So this is the discretized equation of x momentum equation. So we will substitute the guess values of pressure and u velocity and v velocity at the in the initial discretized equation to get the values of let's say u star and v star. Now what happened actually? We will solve for a pressure correction equation based on the output what we get from the momentum equation, discretized momentum equation. Then whatever p dash we get, corresponding p dash, we will get the values of actual pressure, velocity, this thing. So whatever we get, so the initial value minus, sorry, the final value minus the initial value, again we'll check for the residue, and if it is converged, then we will stop it. If it is not converged, whatever output we get, so then whatever the output we get from the first iteration, we will set it as the input value for the second iteration. So that is what we do. Okay, so other one, like for the simplex algorithm, so what we have done actually here, so here after initial guess, so we have one more step where we will find a pseudo velocities. Okay, so pseudo velocities which is of v cap or u cap, or let's say you have other parameters, so pseudo parameters. Those pseudo parameters will go into discretized equation. So here the basic difference between simpler and simplex is, so directly the guess values are going into discretized equation. Here it doesn't go. So before that, we'll calculate the pseudo velocities. from that, basically you are trying to refine the value of guess. So let's say your initial guess value is something 1 meter per second, but the value which you need to guess is 1.2 or 1.3 meter per second. So because of this pseudo velocity correction, so it will nearly approximate it to 1.15 or 1619 meter per second, like that. Okay, so that is the help of pseudo velocity or the additional equations which we solve before substituting it to discrete momentum equation in simplex algorithm. So that is the major difference what we have, and the remaining every parameter, like remaining the steps are same. So here the difference is the initial guess value we are trying to make it as accurate actually, so that we will end up closely to the solution which is obtained to realistic one. Okay, so that is why a pseudo corrections of the pseudo velocity calculation is required. Fine. So this is about simplex algorithm. So now we have a algorithm which is PISO. Okay, so PISO algorithm, as I told you, these algorithm it will behave with respect to time. So previously we haven't seen about the time step. So what we have, so when we need to start, we need to set initial variables. So initial variables are nothing but, let's say, initial conditions. Let's say u velocity, v velocity, and w velocity, pressure. So those things we will do. And then what we will initialize at new time step, which is t plus delta t. So what happens actually? So we will first, if it is started here, so we will set initial variables. Then it is going to the initialization of new time step. So we will calculate. So what happened actually here? U of I plus 1 to the power of n plus 1 minus u of I to the power of n divided by delta t is equal to, let's say, you have u of I plus 1 to the power of n minus u of I to the power of n divided by delta x. So into c. So this is what equation. So dou u by dou t is equal to c into dou u by dou x. So basically one wave equation. So where you can see that here the value of u to the power of n plus 1 is nothing but the initialization of new time step actually. So this is what we have. So once we get this, so we will solve momentum equation implicitly. So implicitly in the sense what? So we will actually perform the implicit equation, then solve the equation of state and update the density value. So this is for the compressible flows, and then solve pressure correction equation. Okay, so once we get pressure correction equation, then we will solve velocity correction equation explicitly. So implicit equations, they are like correctors. Explicit equations, like basically they are predictors actually. So what we get, so from here we are solving the velocity correction equation explicitly, so directly. Then we will solve energy equation implicitly, and then solve the density equation to update. Okay, so after that we will solve second pressure correction equation, then we will solve second velocity correction equation explicitly. So here you can see that velocity equations, so the velocity are calculated explicitly. So here it is calculated 2 times. So whatever the variables we get after the second correction, so we will update the variables and we'll check the convergence criteria. So if the convergence criteria is met, then we will stop. If not, again we'll go for the same step. So the difference between the simple algorithm and this one, so it is very different. So the initialization and after setting the initial values, or let's say the values after we calculate with respect to certain time, what we are doing, so we are actually changing it to one step to other step. After changing it, we are solving it with respect to momentum equation implicitly. So after solving it implicitly, then we will substitute this one in density equation of state, which is P is equal to rho RT. So this is equation of density state. Okay. So from this we will solve for the pressure correction equation, first pressure correction. So here you can see in this method you have two pressure corrections and you have two velocities actually corrections. So the PISO algorithm is getting corrected twice for the velocity, and for the pressure it is getting corrected twice. Okay, that's the difference. So it is a transient solver, and it will give the values which are realistic in nature. So for the difference between the steady state and the transient solvers, when you see the convergence criteria or the residue, so this is less for time and this is residue R. So here steady state let's say it will do like this. When you come to transient, so let's say it is coming like this, and it will show some wiggles. Okay, and after some time it will just reach the steady state. Okay, so that behavior will happen actually. So therefore what is happening, the solving of exact values and realistic values with the initial conditions is very mandatory. So the PISO algorithm is solving the or correcting the velocity twice and pressure twice, so that we end up with accurate initialization, and we end up with accurate solution. Okay, so once it is converged, we will stop it. If it is not converged, then again we will go here. We will not set up the initial values. We will go with the next steps actually. So in the PISO or the simple algorithm, what we have, the guess values will be the next one. No, here not like that. So we'll solve for other time step actually. Okay. So we will iterate with respect to other time. But when you see for the other aspects, so here what is happening, simpler or simple algorithm. So whatever values we have with the ending of first iteration, this will be the input and will be the guess value. Here for the PISO algorithm, what we are doing, we are initializing with the new step. So because simpler, they are the steady state solvers, whereas PISO algorithm, so this is the transient solver. So therefore, we are actually after we are trying to set up with the new step. Okay, so if it is not converged, then whatever the solution we have, we will just leave it there itself, and we will start the initialization or the performing simulation with the new step. So here the n value changes. Okay, so initially n value is equal to 1. So therefore u2 minus u1. Here the next step will be u3 minus u2. Okay, so however we'll be using the u2, but this u3 is different. Okay, so that is the basic difference that we need to observe. Okay, so with this we have seen the algorithms, simpler, simplex, and PISO algorithms in the computational aerodynamics. And with this, we will complete the CFD techniques. Okay, so there is one more, like, which is pressure correction boundary condition. So we'll just see that in the next module. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.